Today's video will focus on the things that we do to try to solve a system of equations using augmented matrices. When we use an augmented matrix, we have a goal in mind, and it looks like this. Let's just pick one that has a 3 by 3 system. And then, I don't know, we got answers over here. This is ultimately our goal. Every time, if we could, this would be exactly what we're looking for to try to get a solution to this system of equations. Of course, some of them, the size may be different and things like that, but this is what the effort's going to be like. We can't always get this. But we'll try to see how close we can get. So, for example, you might see something like this. You might only be able to get that close. Well, in a situation like that, at least we'll know the value of x and y, but z, of course, couldn't be anything in a situation like that. Maybe we'll see something like this. And in a situation like that, we would know x and z, but y, of course, we wouldn't know. It would be possibly, well, in this particular case, y would be possibly anything. So there are various situations that arise. It just depends on the nature of the problem. We might even see something like this. So things like these are all possibilities. I just want to help you understand that there's a lot of different things that can happen, and all of these are the form that we want. It's just we didn't get all the answers like we were hoping to get. And what we're going to do is this section is we're going to figure out what to do with systems that aren't beautiful or perfectly solved like this first one up here. So this one up here is the gold standard for what we want. If we can't get that, we'll get one of these down here. And most of these cases have a situation where we have an infinite number of solutions. So we're going to look at how to deal with those things once we get something for an answer. So let me write down some definitions. Let's start with something called an echelon form. So a matrix is in echelon form if it satisfies the following. So let me put these down. Number one, all non-zero rows are above zero rows. So if you look, let's come back. I got an example right here. As you can see, these 0 rows are shoved to the bottom, where the non-zero rows have made their ways to the top. So that's one aspect that we want to make sure that we have. Each leading non-zero entry in a row occurs in a column to the right of the leading So we have, it occurs to the right of the leading non-zero entry in the row above. What this does is, let me put this down as a thing. This gives us our staircase. So let me see if I can make this. There's a lot of words here, and it makes it complicated. If you look at this second row right here as my example here, all it's saying is when I have the row right above it, it will have a non-zero term that will occur to the left, above and to the left of the other one. This way, as you go down, see, this is another one. This is also an echelon form here. This one occurs to the right of this one. This one right here occurs to the right of this one. That's all that's saying. So as we go down rows, the non-zero leading term keeps moving to the right. Finally, all entries in a column below a non-zero leading So let me see if I can get this one to make sense too. All entries in a column below a non-zero leading entry are 0. Make these letters better. So all entries in a column below a non-zero leading entry are 0. All right, let's take a look at what that means. Let me pull back here and see if I can use one of these as an example here. So let's take a look at all my entries in a given column. Let's use this one here. Here's a column. Okay, didn't mean to move the page. So here's a column once again. So all entries in a column below a non-zero leading entry. So here's, here we are, a non-zero leading entry right there. And then all the entries below it are 0. So let's take a look if that's true here too. Here is our leading non-zero entry. All the items below it are 0. Here is a leading non-zero entry. All of the items below it are 0. So all these things make an echelon form. Basically, what we're going to get is something like this. You're going to, an echelon form could be anything like this. So suppose we have a block, and then we have stuff over here. But I need these things down here to be zeros. And then up here, I don't care what it is, so long as we have something along these lines. So you may have items above these non-zero blocks, but not below. All right, let's do some examples. That's part of the issue with this, is especially the early stuff, trying to describe these things in words is very complicated. As you can see, these are unusual and take a moment for you to think about them. Let's take a look at some examples. Let me see, I have 3 rows, goes like this. Now, for this one, you should know that there is no solution because of the last row. This means 0 equals 5 halves is not correct, obviously. However, this format still fits all of the rules for being an echelon form. So this is an example here. Notice above here, above the leading non-zero term here, I do have stuff, but below, nothing. Below, nothing. I could have had something here if I wanted to, and it still would have been okay. So that's one possibility. There's more possibilities than what I'm going to be able to write here, but I will nonetheless try to illustrate as many as I can as we go through these notes. There's another one that satisfies. Nobody says that the leading terms has to be non-zero. That's not what the rule says. It just says that as long as I have zeros underneath these non-zero leading terms, that's what I want. So these are some examples. You get the idea. Now we go a little farther with the next definition. A matrix is in reduced echelon form if it satisfies the previous three properties for echelon form, but with 2 more properties. So let's go ahead and underline the keyword reduced echelon form. And the 3 above, we're going to add these 2 to get reduced echelon form. The leading non-zero entry in a row must be 1. And 5, each leading one is the only non-zero entry in that column. So we have a little more than we had before. Let me use these examples that I have up here. The problem with this right here is the fact that I have a 2 in that spot. That should be a 1. That would work. That would be part of what I needed. So that's part 4. But then in addition, I have to zero out the things above. Well, not that one, but this one right here would be zeroed out. And technically speaking, I would have to go and zero out these entries here too. So because this 5 halves happens to be the first non-leading zero, or the first non-zero term in that row. Over here, this is pretty close, except this 2 should be a 1, and then this 5 here I could use to wipe out the items above and below it in order to get that diagonal look. So it's a little bit more. What we're looking for here then is something that looks like this. So it looks like what I was saying earlier, this is the gold standard, which is these reduced echelon forms. Let me draw a couple that are not exactly like what I just had there. Might look something like this. That certainly would satisfy our reduced echelon form. Another example looks like this. And if you don't mind, I'm going to stop drawing that little vertical line just because these rules are going to work whether it's an augmented matrix or not. So I'll just kind of drop that for now. Now, what if you're given one that is not in reduced format? So suppose you have something like this. And you want to take that and change it So I want to change it to reduced echelon form using row operations. So the first thing I'm going to do is try to get rid of some of the extra ones that I have. So let's go up here. If you look, this one with 2 zeros underneath it is perfectly fine. It's the only non-zero term in that column, and that was the leading non-zero term. Now I go to the next row and look for the leading non-zero term. That's this guy. It is a 1, checks. However, it's 0 below but not 0 above it, and that needs to happen. And then same thing with this guy right here. This is the first non-zero entry in this last row. I need to take it and wipe out the one above it. So the first thing I'm going to do is take negative R1 plus R2. So then what happens is for the first row I'll get a 1 in the first spot, but this right here, negative 1 plus 1 will be 0. Then I have 1, but when I make it negative, I'll have negative 1 plus 0 will be negative 1. And then this 0 doesn't do anything. And then everything else is the same. Okay, so I'm getting there. Now what I need to do is use this one to wipe out the entries above it. So I'm going to take negative R3 plus R2, and then I'm going to take R3 plus R1. So when I do R3 plus R1, this 1 will wipe out this negative 1. This 1 will get added to that spot. And then for R2, let's see, this will be untouched, this will be untouched. However, this particular one will disappear because negative 1 plus that one will be 0. Let me get those in there. And then I will have a spot in the end here. Negative 1 plus 0 is negative 1. And you can see now it satisfies this because here the leading non-zero term is 1, and underneath of it are all zeros. In the second row, the leading non-zero term is 1, and there are no all the entries above or below it are 0, so it's the only non-zero term or entry in that row. Same here. This leading 1 is the only non-zero entry in that particular column. I apologize if I use the word row. I think somewhere in my speaking I said row instead of column. But just keep in mind the things that we have to do for reduced echelon form. All of the terms that were given in terms of column. Let's try one that's a little more complicated. So let's put the matrix in reduced echelon form. So we have 1, 3, 5, 3, 5, 7, 5, 7, 9, 7, 9, 1. All right, so what I'm going to do is start over here all the way to the left and look at this particular element here, this entry, this 1. I'm going to use it to wipe out the entries below it. So I'll do negative 3R1 plus R2. And at the same time, I'll do negative 5R1 plus R3. So one thing I know I'm going to get is this. That was by design. The rest of it, let's be careful in how we do it. So I did negative 3R1 plus R2. So negative 3 plus 5, or negative 3 times 3 is negative 9, plus 5 is negative 4. And then negative 3 times 5 is negative 15, plus 7 is negative 8. And then negative 21 plus 9 is negative 12. And then for row 3, let me see, I know I took that one out, but negative 5 times 3 is negative 15 plus 7 is negative 8. 5 times negative 5 is negative 25 plus 9 is negative 16. And then negative 35 plus 1 is negative 34. Now, what I want to do next is I want to do this guy right here and wipe out the items below and above it. So as it stands, being a 4 is not the most desirable thing there because I'll have to adjust row 1 to get that to work. So it's always best if you can make the item a 1 as soon as you can. And I can do that because if I divide this row, this second row, by negative 4, I will have a leading 1. So let's do that. So I'll take negative 1/4 times row 2. Of course, nothing else is affected by this move. And there we go. Now I'll go ahead and wipe out the 3 that's above the 1 and the negative 8 that is below the 1. So to get rid of that 3, I'll do negative 3 R2 plus R1. So negative 3 times 2 is negative 6 plus 5 is negative 1. And then negative 3 times 3, negative 9 plus 7 is negative 2. Of course, the second row is unaffected. But to wipe out this negative 8 down here, then, I'll have to take 8 times the second row and add it to the third. So 8R2 plus R3. And of course, that wipes out that entry. Well, that's nice. 8 times 2 is 16, so it actually wipes out that entry as well. And then 8 times 3 is 24. 24 minus 34 is negative 10. Now I'm almost done. I have actually 2 more steps. first thing I'm going to do is change that -10 in the bottom right corner to a 1. Now, note, if this were an augmented matrix, we would have no solution just because of that 1 way down there. And then finally, I'm going to use that 1 to wipe out this 3 and this -2. So I'll do 2R3 plus R1. And notice these zeros mean that nothing will be touched before that, just this column will be affected. And at the same time, I will do -3R3 plus R2. And what we have then is the completed form. Let's take a look and make sure. We already know about the echelon form. We've got the leading non-zero terms going down in a stair-like fashion. But then let's just make sure that each leading non-zero term only has one non-zero entry in its column. So if you look at this one, it's the only non-zero entry in the column. Now go to the next leading one, this guy right here. It's the only non-zero term in that column. Now drop down and go to the next leading one. Here it is. It's the only non-zero term in the last column. So that brings us to a point. What we're going to do is start describing in great detail each of these steps that we're doing so that we can use them later on to develop incredible properties to be used, theorems and whatnot, to solve systems of equations, or if we can't solve them completely, at least get a handle on the types of solutions that they have. So that brings up this important concept. Let's go back to the start again. And let's look at the very first thing that we did to try to clean this stuff out. The first thing we did was we took this one, I'm circling it, and we used it to clear out all of the members that were below it. So we ended up with something like this when it was done. Now let me go ahead and copy the rest of the items that we have. Well, I know what they are. I'll just write them down. This was after the first step. So that thing that I circled there, that one, is referred to as a pivot. Or more precisely, this spot is called a pivot position. And what it does is it uses itself to wipe out the entries below it. Or in the case of the next step right here, this -4. Now remember, I changed it to a 1 and all that stuff. That's not the important thing, really. What's important here is the spot that it was in. This particular spot was going to end up being non-zero when all was said and done. That -4 will pivot up and down to wipe out the entries below and above it. It's no different than if you've ever played basketball and you've heard of the term pivot, where the guy goes, he has one foot stuck to the ground and he turns left or right to try to pass the ball to somebody or shoot the ball. That's probably what it has to do with as far as the name is concerned. This is going to pivot up and down to blow out the non-zero terms and zero them. So we did that. And the beauty here is as you go in a staircase fashion, you're not going to ruin the previous columns. They'll be set. So what we did is when we wiped this out, we ended up with the following. I think we had, let me grab it from up here. There it is. this guy right here was after we had done a bunch of stuff. So we have 0, -1, -2. Then we had 1, 2, 3. Now let me come back and see what else we had. 0, 0, 0, -10. Now, in our next step, we did not go and do anything with this 2 or this 3, of course. What we do, think of it as going by rows. We took care of a pivot position in the first row. We finished it. Then we moved to the second row and took care of a pivot position. Now move to the third row. The only possible pivot position is the first non-zero entry, and that's this -10. And then what we did after we did that, we used this -10. First we turned it into a 1, and then we wiped out the items above it. So it pivoted only straight up. And that's how we arrived into reduced echelon form. Let me put a definition down for this just to make it specific. The reason why you put precise definitions down is because later on we'll be using these definitions to prove theorems and things of that nature, and you have to be very precise. So let's do a definition. What is a pivot position? Well, a pivot position in a matrix a lot of times we'll give matrices names, and it will always use capital letters for a matrix name. So just like anything else, it's like saying take a real number X and you do this and this with it, whatever. This is the same kind of thing. I'm just giving it a name for convenience. So a pivot position in a matrix A is a location So this is sort of complicated. A pivot position is not something that you can locate immediately. It depends on how the matrix shakes out. So let's go back to the previous example. You know what the pivot positions are only when you're completely done with the matrix. I mean, for certain. So we knew this was a pivot position, this was a pivot position, and this was a pivot position. They're all the places where the leading ones would have occurred. So in the original matrix itself, let me come back here. Notice those locations. So let me go back. That means there was one here and there was one here. You probably would have hoped that this 9 would have been a pivot position, but you didn't know that until you got all the way to the end. So that's all they're saying, is you can't necessarily see pivot positions when you first look at a matrix. You only see them when it shakes out at the end. So basically what we're going to have is this. We're going to start with A, and we're going to do a bunch of stuff to it until we arrive at a final form called U, let's say, and U is that echelon form. Alright, suppose now you have a matrix, I give you a matrix, and you go and you convert it or use row operations to arrive at an echelon form. Let's call it U1. Another guy goes and does the same thing, but he doesn't do the same row operations. Let's say he ends with possibility of having a different echelon form. Is that possible? And the answer is no. What that means is no matter what you do and you arrive at U1, and no matter what they do and they arrive at U2, U1 will equal U2. As long as you're using row operations, it doesn't matter what you do, you will end up at the same spot. We, right now, do not have the means to prove such a thing. We have to wait till we get to a topic called vector spaces later on. But for now, just know this, that there is only one answer. When you're asked to give the echelon form, the reduced echelon form, sorry. I should have put this. I think I made a mistake here. These echelon forms can be different. So these are reduced echelon forms. Sorry, that was a gross problem with mine. The words that I was using. So we use a reduced echelon form of A as unique. That's all I'm trying to say. No matter what you do, no matter what somebody else does, if you do a matrix in two different ways, you get what you think should be two different echelon forms, they'll end up being the same. We'll have to wait till later in the course to prove such a thing. Let me do an example.
So if you don't come down?
All right, here we have an interesting matrix. If this were a system of equations, you would have an x, y, and z for both equations, except the z term is missing. So I guess we only have x and y's. Well, let's go ahead and do what I need to do to get this into reduced echelon form. So I'll take negative 2r1 plus r2. Notice this one right here. If you have a non-zero term in this spot right here, we could call that a pivot position automatically. So I'm going to use this pivot. So that's an easy one to figure out. That's always going to be one if it's non-zero there. I'm going to use that to wipe out the 2 underneath of it. Let's see where we ended up at. So negative 2 times 4 is negative 8, plus 7 is negative 1. The column of zeros doesn't do anything. Negative 14 plus 10 is negative 4. And now I've almost got the staircase method that I want, except the problem right here is this negative that's right there. So I'm going to divide by negative 1. Well, I think I'll divide by negative 1 at the very last step. What I'm going to do next is use this negative 1 to wipe out this 4. So I'll do 4r2 plus r1. And so negative 16 plus 7 is negative 9. I'm almost done. All I got to do is change that negative in front of the 1 to a positive. And so now let's take a look at what we have as far as answers are concerned. This could be the x column, the y column, and the z column. So we can see that x has to equal negative 9, y equals 4, but z is not anywhere listed. That means z can actually equal anything. Because it's not even listed among the equations. So z can obviously be anything it wants to be. And so our solutions look something like this. When I write my answers, it'll look like this. I'll have x, y, z. Let's call this the answer. I know only the value that x and y have to be. So you can see this is called a free variable. That means that it can take any value. So that's how we are going to handle situations that have an infinite number of solutions. I can't put any particular number in for z. I just know that this particular answer will work no matter what value z is. So usually the ones, not always, but usually the ones that have some sort of an infinite solution are the ones where you have a different number of variables than equations. So if I have only 2 equations and 3 variables like this last one, you could see that's a system that has more more unknowns than equations. So you shouldn't be able to expect that that would have a unique solution. On the other hand, you might have a situation where you have more equations than unknown quantities. And in a situation like that, you might expect that some of the extra equations weren't necessary. So anyways, the best thing to do is some more examples to show you. And when I just say solve, keep in mind that I've already taken a system of equations and have converted them to an augmented matrix. Once again, I'll start with my first pivot position, which is this 1 here. And I'm going to take that 1 and use it to destroy the 3 that's underneath of it. Now notice that makes this -2 times -3 be 6. That'll wipe out the number underneath of it as well. But over here it won't. Here I'll get 3 minus 2 will be 1. Well, that's nice, because it puts a 1 where I want it. And then finally, -9 plus 2 is -7. Now it's almost done. As far as getting the form that I want, I'm going to go and wipe out this particular entry right here using this 1 here that is in a pivot position. So I'll just simply add row 3 to add row 2. I'm sorry, row 2 to row 1. Let me see, I get a -4 there. All right, now if I think of this as having an x and a y and a z, I know that z equals -7. However, I have in the first equation this first equation here tells me that x minus 2y equals -4. So you get to decide here what you want to be a free variable. You can see I do not have an explicit solution for either x or y. They're defined in terms of each other. So what I can do, when I write my answer, I can do this. I can do x, y, z. Here's one particular way that I could have written an answer here. You can see that y is a free variable if I went and solved the equation above for x. Or if instead take that equation above here, suppose I had solved for y instead, I would have gotten 2y equals x plus 4, or in particular, I could leave x be x, and y would have been x plus 4 divided by 2. Z was stuck at -7. In this case, x is free. So there's 2 different ways to write the answer, but they both mean the same thing. X and y are related by being on a line. So I don't know, one is just as good as the other one. Somehow I like the first one better, but it really doesn't matter. Either one will be fine. let's do another a longer looking one. And like the other one, I'm going to first try to get this into reduced echelon form before I do anything else. So here, I think it's pretty easy to see the pivot positions are all located fairly quickly. Right here, this already did its business, so that's not going to be a big deal. This one right here in the second row is our next pivot position. I can use that to take out the 2 above it. And if I go down a row and go all the way over to its first non-zero term, there's its pivot position all the way there at the end. So I really only have one thing I can do because this one has zeros up here. All I can do is take and clear out this 2 and I will be in reduced echelon form. So I will take negative 2r2 plus r1. So let's see what happens in this case then. So 12 minus 5 will be 7. Here, 6 minus 6 will be 0. And of course the last column, the last spot is unaffected. And then negative 4 minus 5 is negative 9. And then now I have it in reduced echelon form. Now, how do we write an answer to this? Using x, y, and z is fine when we only have 3 variables, but what do I do when it starts to get longer? I guess I can go w, but then it's going to just get ridiculous. So after a while, you'll learn that this is probably the best way to do it. Let's call our unknowns with a subscript, and then I don't have to invent letters for them. This is what you'll see most often in the textbook, is they'll be doing this instead of an x, y, and z. I just use x, y, and z because I thought it was more familiar and comfortable with the students. But let's take a look then what we have for the first equation. So this is the first row, remember, gives us an equation. Let's write that out. I have x1 plus 7x3 equals negative 9. And then my second row involves x2, 3, and 4. So I have x2 minus 6x3 minus 3x4 equals 0. And the last equation is simple here. This third row gives us that x5 just simply equals 0. So when I write my answer, there will be a 0 in the last spot. Now what I can do with these is, here's the plan. Notice that x3 is involved in the first 2 equations. So I can use x3 as a way of describing my answers. So the first equation can look like this. x1 can equal negative 7x3 minus 9. And then x2 can equal 6x3 plus 3x4. And then of course x5 is taken care of. So when we write our answer, it looks like this. x1, x2, x3, x4. Didn't go far enough, did I? x5. Let me change this thing to accommodate all of those variables. So x1 was negative 7x3 minus 9. x2 was 6x3 plus 3x4. x3 will just be itself. x4 will just be itself. And then x5 was 0. And then what I need to say over here is that x3 and x4 are free. So once again, as you can imagine, let's go back to the problem here. I had 5 variables, but I only had 4 equations. So I didn't have enough equations to expect that I should get a unique answer. Now we're going to try something a little bit different. In the last couple of examples, I had a solution that had free variables. That means there was an infinite number of solutions for all of those examples. We would like to know kind of when we have an exact answer. So let's take a look at some situations here. So there's what I have. I have essentially an echelon form of this thing. I want to determine if I have a unique solution or not. Well, as you can see here, this third row doesn't do much for us. It's almost as if it was too many equations for the number of variables that we have. Notice since this block is non-zero, I can use it. It's a pivot. So I can use it to wipe out what's above it and arrive at the following. So I'll still get, and I for some reason I keep making these too small. Let me change that 0 to my block. And the stars, I'm not going to label them different or anything. I just want you to know the basic structure. So I am able to get something like this, and that is a unique answer. We will now know what the x value will be because it will equal star, whether it's 0 or not, it will equal that. Same thing here. So this here would be an example where you would get a unique solution, even though you do have a row of zeros at the end. So yes, there is a unique solution. Right there. So we want to determine if there's a unique solution. And I'll use the same thing I did before. Blocks will be non-zero numbers, but stars can be anything. So here I have a three rows, 5 columns. And it looks like this. I'll have a block, zeros underneath that block, star, zeros underneath that star, star, block, 0 underneath of it, star, star, block. Remember the blocks are non-zero. And then I'll have a final column. Well, I can see here, here's what we have now is we have x1, x2, x3, and x4. So I have 4 variables. Now, with these spots here, I can see that I have a pivot position here, but it's already done its job. All I would really have to do is divide by block to get a 1 in that spot. I have a pivot position here, and I have a pivot position here. As before, I can use this non-zero pivot to wipe out what's above it. Similarly, over here, I can use this non-zero number to wipe out what's above it. And so when that's finished, I can get something like this. Let me see, I have 3 rows. I'll only put zeros where I know that they are actually going to be. So let's see here. X4 I would have an answer for. X3 I would have an answer for. But what about X2? I do not. In fact, what would happen here in this first equation, you would see that you would get X1 plus maybe something involving X2 equals a number. That means that X2 is free. If it's free, that means there's an infinite number of solutions. So we do not have a unique solution. So to determine if the system has a unique solution, no, the system does not have a unique solution. So that's the interesting thing about this, is many times you won't be able to just look at something. You'll have to do some mental gymnastics to finally get at the answer. Next, consider the following. Here we have x plus 3y equals 2 and 3x plus hy equals k. I don't know what k and h are, but what I'd like to do is the following. I want to choose h and k so that A, we have no solution. There's three parts to this actually. B, a unique solution. And C, more than one solution. Of course, in my experience, more than one solution means it's going to be infinite. So these are three parts. Let's take first, before I do anything, I'm going to convert this to a matrix. Now, my job is to figure out values of h and k for each of these processes. But first, what I'm going to try to do is get it into as close to reduced echelon form as I can. So I'll wipe out the 3 that is underneath the 1. So when I did that, then I have negative 9 plus h, so or h minus 9. I like the looks of that better. And then over here I have negative 6 plus k, so I have k minus 6. Make that 9 a little better. Now let's start here. For no solution, the situation where we have no solution was when this entry was 0, but this entry was not. So if h was to equal 9, but k was to not equal 6, then that would tell me that I would have a 0 in this spot, but not a 0 there. So that takes care of part A. There's the no solution case. For part B, a unique solution. Well, if I wanted a unique solution, then I should have a non-zero item right here, and it doesn't matter what's over here, because if whatever this non-zero item for h minus 9 is, I'll be able to divide it to get the value for y. So in that situation, we simply need h to not equal 9. I should be, yeah, that's fine. Now part C, this takes care of all the rest of the cases. If I want there to be more than one solution, the only way for that to happen is if I have a 0 row at the end. Then I'll have x and y involved up here, and you'll have an infinite number of solutions. So the only way for this to happen, to zero out this row, is when h equals 9 and k equals 6. As a note, let me throw something up here for a second. Here is this an augmented matrix that represents a system of linear equations that has no solution. All right, however, though, if you were to think of these as x, y, and z, I know that x must be equal to 10, but I have no idea that y or z would be equal to. So the point I'm making is that y and z are free, but there is no solution. So the point I'm making is you can have free variables without actually having a solution. Just because you have an infinite number of possibilities for the variables does not mean that any of those possibilities will be an answer. So the point is that you can have an infinite number of possibilities with no solution. All right, for my next example, I want you to consider a system of linear equations that has a 3 by 5 augmented matrix and the fifth column is a pivot column. So what kind of a situation do we have then? 3 by 5, so I might end up with something like this. And I really don't care about the rest of the entries, but I have 5 columns in total. So there's a final column. Let's have something like this. So if the fifth column is a pivot column, that means that I would have had to have had zeros all the way until I got to it. Well, then we can see automatically if I have all zeros until I got to the pivot. And the pivot position could have, the pivot spot could have been anywhere, but when when all is said and done, the way I said that was wrong. The pivot position actually is locked into this place based on the way that we do things. But all I'm saying is the non-zero term could have appeared in other spots, but through the sequence of row operations and whatnot, the non-zero term would have had to have landed down in this corner. So it would have to be the first non-zero entry in that row. And you can see in this case, there is absolutely, definitely no solution. Keep in mind, I'm going to use phrases like pivot column. When I use the phrase pivot column, it simply means that the pivot position is in that column somewhere. Where the location is won't be known until you solve the whole thing. But let me throw a theorem up. This you can think of as an existence and a uniqueness theorem. Here it goes. A linear system is consistent if and only if the rightmost column is not a pivot column. So no pivot in the very last column. And if that's true, then we will have a consistent system, which means we have at least one answer. It may be an infinite number of answers, but nonetheless, we have at least one answer. So let's take a look. Let me do a proof. Assume the rightmost column is a pivot column. Well, what that means, if that rightmost column is a pivot column, then in its row, it has to look something like this. So that's the rule of being a pivot column, is whatever is in the pivot position has zeros in front of it. And you can see that it's going to have no solution. And so, and you can reverse this too. If you say the system is consistent, then this situation cannot happen. And so the rightmost column could not be a pivot position, or could not be a pivot column. Let me do something that's called a corollary. Usually when a theorem you prove something, a corollary proves a little more, or proves something that it uses the theorem that you just used. So let's write this down. A system of linear equations has a unique solution if and only if. If you ever see IFF, it's a shorthand notation for if and only if. So it's nice for notes, or especially if you're doing note taking, if you have things like this to save yourself time, because a lot of times it's hard to keep up in class. So there's a whole slew of things like that. If you go higher into math, you'll see what I'm talking about. So anyways, we have a unique solution if and only if every column in the coefficient matrix is a pivot column. So when you think about this, if every column is a pivot column, that means we had to end up with something like this. Or better yet, it might be this. If every column is, so the next column I'd have to have a pivot. The next column I'd have to have a pivot. Every column in the, in the coefficient matrix is a pivot column. And then along the end here, I really don't care about these. I get something like this. And same up here. We'll just put a big star there to indicate, well, I don't care what's there, but underneath of these things, you know, you get zeros down here and zero. You get the idea. Zeros underneath them, because they're pivot columns, you have to have zeros to the left and underneath of them. So I can, though, since they are pivot items here, this is non-zero. I can use it to wipe out what's above it. I can use this to wipe out what's above it. I can use this to wipe out what's above it. So you can see I'm able to get to the following. Block 0, just by doing row operations. Try to indicate something. Well, hopefully you get the idea. And whatever's on the other side is unimportant to me. Just a bunch of stars over there. So we can use row operations to clean up the rest of the matrix and get one in reduced echelon form. So that's all it's basically saying, is able to get us a reduced echelon form. We have a perfect diagonal of non-zero entries. Well, then this is nice. All I got to do to get x1 is divide by whatever that block is. All I got to do to get x2 is divide by whatever that block is. So I can not even do this. I can change all of these to ones simply by dividing out these items. And so when you do that, I'm able to get something like this. And this is, we'll have ones along the diagonal. And we'll have zeros elsewhere. And you'll have numbers over here. So you can see this implies that we have a unique solution. Now, if you recall, the theorem was if and only if. Well, true to form, I could change this arrow to an if and only if arrow, because if instead I start at the bottom here, and let's say if I have a unique solution, I would know the value of each variable. That means I could set up a system or an augmented matrix immediately like this, since I know the answers to each of the variables. Well, from then, I could go and reverse the row operations to put it back to the original matrix that I had. Even if I had rows of zeros underneath, which could I have that? Yes, I could have rows of zeros underneath. It wouldn't have mattered. The system would have had too many equations in that case, and they simply got erased out. So you can see that this is what we're looking for. If we can get a pivot position in each column, you know you're going to have a unique solution. This leads to a definition. A system of equations. And this is interesting. I'm not even saying linear equations, because this statement is true for a broader collection of equations than what we have. But it really doesn't matter. What's important is we have a system of equations, and it's underdetermined if there are fewer variables than equations. In a situation like that, the best you're ever going to be able to do probably is to get an infinite number of solutions, but you won't be able to get a unique solution. The system is overdetermined if there are more equations than variables. So with that in mind, it's overdetermined, meaning you probably have extra information that wasn't necessary. And so what usually happens in those cases is you'll find that you'll have rows that will just zero out. Let's take a look here. Here is a classic example of an underdetermined situation. Here, 3 variables. Each column, if you want to think of it this way, is a variable column. So the first column is x, the second column is y, and the third column is z. 3 variables, 2 equations. So in this situation here, we are underdetermined. On the other hand, I can simply reverse things a little bit. And in this case, then we just have two variables like x and y, so two variables. 3 equations. This is overdetermined.